today's notes here, what we're trying to do is boil down how do motion graphs work on one page. So the first thing is let's kind of review the quick definitions. How do you define velocity? You guys remember? What's the equation for velocity? Velocity is like speed, but it's speed with direction. So how do we say that? Is velocity distance over time? That's speed, right? So what do we call velocity? Velocity is our what? Our change in position, right? Our displacement over time. Our delta x over t. If we want to expand that, that's the same as x final minus x initial divided by time. So notice that by taking into account each position, we can also then define direction. Units, what would the units be? Let's add this on over in this column over here. Units would simply be what? Meters per second. So it looks just like speed, but it's speed with direction. Acceleration, that's a little bit trickier because it's the rate of change of a rate of change, right? It's how fast you're speeding up or slowing down. But in physics, we want to have a precise definition. So how would you define acceleration? Acceleration technically is not just speeding up and slowing down, it's your change in velocity with respect to time. You take your final speed, your final velocity, subtract your initial velocity. Let's say your car was going 50 miles an hour, you set up to 60 miles per hour in 2 seconds, right? Then you could actually calculate your rate of acceleration. It's a change in 10 over 2. It would be 5 miles per hour per second. Usually the standard units, though, would just be meters per second, or meters per second squared. Next, we're going to look at trying to summarize the 3 types of motion graphs there are and compare and contrast them to the 2 main types of motion. So maybe to help you visualize this, we're going to look at what's called constant velocity versus constant acceleration. And the way you can picture this is think of your car. When in your car would you ever drive at just a constant speed for a long period of time? Can you think of this? Anyone going on a road trip this weekend? Woo, we're out of here. Okay, yeah. What do you do in your car when you want to lock it in at a steady speed? You set the cruise control. In fact, by constant velocity, write cruise control to help you summarize that in your own words. Cruise control. Think of it like you're locking in your car at 60 miles an hour so you don't get a speeding ticket. How about when would you want to accelerate constantly? Can you think of that? Usually you accelerate constantly when you're at a what? When your car is sitting at a stoplight, right? And the light turns what? When the light turns green, then you take your foot. When the light turns green, you take your foot and you stomp on the pedal. This is supposed to be the gas pedal. I don't know how to draw that. That's okay. And you're just trying to speed up at a nice, smooth, steady rate. In real life, you're not a robot. You might stomp on the pedal harder or lighter, but ideally, it should be a nice, smooth acceleration to give you the best gas mileage. And in real life, there are 3 types of ways you can plot motion, and all 3 are related to each other. So the first one is called the position versus time graph, or the distance versus time. You can think of it that way. So maybe the easy way to picture this, my little secret shortcut way, is I call this the GPS graph. This is supposed to be a map of the United States. Good thing I don't teach social studies. There you go. That's supposed to be like a little GPS there. How about this? Can you picture this? What would a position versus time graph look like for an object moving at a constant speed? We kind of gave you a little sneaky peek there, yeah? It's going to look like what? Okay, it's going to be a linear relationship. Good job. So here's a way to picture that. Little simulation we're going to use later on called the moving man. So exciting. There's a dude here, and you can make it move. Wow. So the first thing I'm going to do is I'm going to put him on cruise control. Let's give him a velocity of 2 meters per second, positive. So what does that mean? When I hit go, every second he can travel 2 meters per second. Wow. Is that the most exciting thing ever? We'll pretend. What would negative 2 look like? Can you guys picture this? Negative 2 is the same thing, but he's going which way now? Backwards. You see that? Speed with direction. So notice what's different here is the position graph goes backwards. It shows him going forwards to the house and then coming back. You see that? And we can actually rewind this and watch this in slow motion. Wow. So notice here, he's going forwards at 2 meters per second, but the slope here is going upwards at a steady rate of 2 meters per second. Acceleration will be what if you're not speeding up or slowing down? Right here. Can you see this? The acceleration graph's a big fat what? 0. You see that? So let's go ahead and summarize that on our little note page. Let's sketch in what a constant velocity graph will look like. So here, let's say we have our origin, our start. This is x in meters. Time is in what? Seconds. So for a constant velocity graph, if we're going to sketch this in, it would just look like a straight line going up and to the right is a way to visualize this. And let's call this, let's go ahead and label this relationship. This is linear. It's a straight line going up and to the right. And that's because in equal intervals of time, you're just going up and to the right. If you have a ruler, go ahead and use your ruler to help you draw straight lines. Otherwise, you can use like the edge of your eye to make it easier. But for part of your course supplies, you should have a ruler. Make your life easier. So make sure to pick one up there. That way on quiz time, test day, it's a lot easier when you're drawing these out. Next, what does the velocity versus time graph look like? Secret shortcut way to remember what velocity would look like in your car. Actually, you know what? You tell me. How can you figure out how fast you're going when you're in your car? It's actually pretty important. You would look at your what? Your speedometer. So this is kind of like a graph of your speedometer. And you're like, wow, this is really nerdy. When would you ever like have a graph of your speedometer? This is like your speedometer. Except technically your speedometer does not measure velocity. Your speedometer would have to give not only your speed, but also your direction. That's velocity, speed with direction. So it'd have to be like a speedometer with a compass, and then maybe go negative if you go backwards, something like that. So actually, this is very practical. There's a thing in your car that most people have now, or on your phone. It tells you where you are, where you're going, how fast you change where you're going. What's that called again? Your GPS system, yeah? So you can actually pull up on your GPS a travel log, which will actually show a graph of your speeds over time there, right? And I've actually heard stories, this sounds kind of crazy, where some people's parents, they'll actually pull up the GPS log. Oh, your parents do that? Okay. To see where you've been and if you've been speeding in the neighborhood and all that. Yeah, there we go. And I would say it's okay if your parents do that, but they should still talk to you. You should have like trust relationship there, right? Though I bet if you pull up like your mom or your dad's like driving log, you would see that they speed all the time there. For velocity versus time graph, this would be in meters per second. This is in seconds. What would the graph look like? It would be a nice what? If you locked in your speed, it would be a what? A constant flat line, right? You see that? You're not speeding up or slowing down. You're on cruise control. Make sense? And where this is going to be really cool is, I think, in the future, when we start having cars that can drive themselves there. Next, last type of graph, acceleration graph. What the heck is an acceleration graph? What are the units? It's in meters per second, or meters per second what? Squared, right? Yeah? And then time would be like in what? Seconds, right? So this would be like a graph of your gas pedal. Think of it that way, like your gasometer. That sounds kind of weird. So this is you stepping on your gas pedal. This would be like your gasometer, how much you're stepping on the gas. No such thing. And you're like, wow, that's really nerdy. When would you ever graph how much you're accelerating? Great question. Most of us would never do that. But later on, when we talk about the physics of racing and we do this awesome physics field trip where we go to Chicago Indoor Racing, having this data to look at in which part of the race where you step on the gas pedal, how much, is very useful for a race car driver there. And one of our former alumni, Cooper McNeil, professional race car driver, he actually has these sensors in his car. It's awesome. It measures brake pedal pressure for negative acceleration, gas pedal pressure, graphs his position versus time for each part of the race on each part of the turn, and it tracks in 2 dimensions because, real life race car track turns in circles, etc. So anyways, if you're not accelerating, you're moving at a constant velocity, what does your acceleration versus time graph look like? It's a big fat what? 0 there, right? It's a flat line. So we're just trying to intuitively get a gut feel before we start putting all numbers to these graphs here. So maybe a quick review there, because this was like kind of nerdy, right? And like abstract. I'm going to go ahead and reset this really quick by clearing this out. Let's go ahead and set the velocity to a nice easy number. I'm just going to make it 1 meter per second. If I hit go, that means I'm locking this in at a steady 1 meter per second. Notice the position versus time graph increases at a linear rate, and the acceleration stays at 0. So this is a pretty simple motion. Notice all 3 graphs are related to each other, but they're different ideas. One is where you are. Go ahead and rewind this and play it back in slow-mo. This is where you are at any point in time. One is how fast you change where you are. The other is how fast you change how fast where you are. Someone's like, this sucks. Why would you ever do this in real life? Because we have nothing better to do than to make nerdy graphs of motion, right? Very practical. In real life, let me show you a simple example. In real life, you never just drive at a steady speed. You might take off from a stoplight, so you're flying along, and then suddenly you decide to like slow down and then drive backwards because you're crazy, and then you go forwards, and then there's a stoplight, and then there's a Hinsdale cop, so you go stop, right? It's very complicated, right? So how the heck can you figure out exactly where you are at any point in time, how much distance have you covered, right? How fast you change where you're going, where you need to make your next turn, etc., right? How do you tell like a machine to do that? It's like magic, right? This is how you do it. You put in the basic definitions of motion. And in a second, I'm going to show you how these graphs are related.